Okay, friends, welcome back. We're going to take a look at optimization problems. They're also known as max-min problems today. These can be really tricky, but they're also so good for giving you chances to practice modeling and representing your ideas in multiple ways. So let me show you one of the problems we're going to look at today. And we're going to start off with a little experiment and help you visualize this. So Farmer Bob has a total of 2,400 meters of fencing materials. Determine the maximum area that can be enclosed by all three adjoining fields. So what I want to do is go over to Desmos and sort of graph the situation. So remember, that we had this situation where we had this these fields, and we have a total of 2,400 meters of fencing to go around. So what I'm going to do is I'm going to approximate the different possibilities of what fences could be. So just as a start, I'm going to start off with 100. So if that's 100, all these lengths would be 100. So that would be 100. That would be 100. So I have a total of 400 of fencing this way. So that would mean I'd have 2,000 left over, which would mean this would be 1,000 here. And what I'm going to do is I'm going to graph this with width on the bottom and area going up. And I'm going to plot my first coordinate here at 100 and one. Let's see if that will give it to me. Yes, it will. So 100 times 1,000 is actually, I'm just going to lose that multiplication symbol, and we're going to go to 100,000. Okay, so there's my first coordinate. I'm going to do the same thing for 200. Let's say I'm just guessing. So 200, 200, 200, 200. So that'd be 800. So I'd have 800 used that way, which would mean I'd have a total of 1,600 left from the 2,400. Okay, so if this is 200, 200, 200, we have 800. So that would mean that this would be 800. Okay, so if I added those all up, 800 plus 800 is 1,600 plus another 800, we would have 800 times 200, which is 200, and it would be 200 times 800. Okay, so that's higher. Okay, let's try, I don't know, let's try 300. Okay, and we could test this value as well. So I'll make that 300. So that's 300. And that's 300, 300. So I have four 300s, 4 times 300. I know this is getting a little bit messy, but if this is going to be 1,200 here, so if that's 300, then that would have to be 600 and 600. Okay, so I trust that you can kind of, test different values and go, I'm going to go, why isn't that? Oh, so I'm going to go down one. That's going to be 300, and that's going to be 300 times 600. Oh, it was higher still. Let's try one with shoot. Where did I get to? Okay, there we go. Okay, so we're just going to clear the screen. We're going to do it again. This time, let's do this with 400. So it would be 400 times 4. So that would be a total of 1,600, which would mean if this is 400, 400, 400, 400, I have 1,600, and I have 800 left. So this would have to be 400. So the, oh my gosh. There we go. Okay, so we're going to go, the width would be 400, and then the area would be 400 times 400, which gives us, oh, notice that's interesting, it got smaller. So in terms of finding the best possible thing, it looks like it's somewhere in there, okay? And we could test values all day long to find that, but we're not going to do that. Let's hold on to that just for a second. Now let's get to the problem. Okay. So what I want to do is walk you through how I might solve this, okay? So first off, it begins with a really good drawing and recognizing that the area equals length times width and the perimeter equals 4 W's plus 2 L's, which is what we've stated. Now, the question says that we need to maximize the area. So what we mean by maximize the area is basically this graph here. Like we can see, here's area, here is the width. So we're trying to find sort of that top spot, and it looks like it is, because it kind of looks like it's doing something like that. Okay, so what we're going to do is we're going to do this guy here, length times width. Notice that when you have length times width, that's too many variables. So we are going to get rid of one of the variables. This is length and this is width. And so I've recognized that there's a problem here. I'm going to be noticing and wondering. This is the competency 4A. We're trying to create conceptual understanding by noticing and wondering. And so I'm going to start off with this statement here and isolate for L. I could have isolated for W as well, but I didn't want to divide everything by 4. So that's what I did. Now what I want you to do is look at this. This is 1200 minus 2W times W. That's the equation. I'm going to go back here and I'm going to type that in here. And I think it was let's get that equation in, let's hide, okay. So it's going to be bracket 1200 minus 2x times x. Watch what happens. Can you see that that parabola goes perfectly through that? And here's what we know. What do we know about the slope right there at the maximum? We know it's 0. So now when we come back here, all we need to do is take the derivative of this. Is this a good time to take the derivative? Please say no. We would want to expand first. Otherwise, you have to use the product rule, which is not a great idea. Okay, so let's not use the product rule. So I'm going to expand that out. I'm going to take the derivative, 4w plus 1200. I'm going to set it equal to 0 because the slope is 0 at the maximum. I'm going to rearrange, and w equals 300. So if w equals 300, I could figure out what that value is. 4 times 300 is 1200. So we could easily determine what L is in that case. And in this case, it's 300 by 600. And when we look at our experiment, we had the 300, and the height was at 180,000, which was the highest piece there. Okay, so that's obviously a really tricky problem, and I trust that you can solve that on your own. Okay, what I'd like you to do right now is clear, is pause the video and try this question on your own. Okay, welcome back. I trust that you spent at least 10 to 15 minutes on this problem before looking at this video. Fortunately, this is not erasing, and I don't know why, so we're going to be stuck with it. Okay, so in this problem, we have two numbers, two positive numbers, whose product is 10,000. So I'm kind of thinking A plus B equals 10,000. Okay, and then I'm thinking whose sum is a minimum. That means sum, so that was supposed to be multiplied, whose sum is a minimum. So I'm going to say A plus B equals a minimum. Okay, so what I'm picturing here is sort of some graph, some situation where all the numbers are leading off to positive, negative, infinity, but there's a spot that's actually the absolute smallest number you could, positive number you could get. So let's see what happens here. Okay, so obviously let's start off with two numbers that multiply to 10,000. I sure hope you pause the video. Do not watch this. Do not just watch me do this. You're not developing any critical competencies other than trying to figure out what I'm doing. Okay, so then we're going to set the minimum equal to A plus B. This is all we need. What we need to do is recognize we have too many variables, so we're going to have to rewrite AB equals 10,000, which I've done right here. So I've rewritten it as A equals 10,000 over B, and I'm going to sub it in right there. Is this a good time to take the derivative, or should I make a common denominator? Pause the video and think about it. Please do not make a common denominator. You do not want to create a situation where you need a quotient rule. So let's just stay in this realm here. I'm going to rearrange this using exponent laws. And at this point here, you can see that that's a pretty straightforward derivative. So the derivative of 10,000 b to the negative 1 is negative 10,000 b to the negative 2, and the derivative of b is 1. Now we're going to set the derivative equal to 0, and we do that because we're looking for the relative minimum. Okay, so I've done that. I'm going to take the 1 to the other side eventually. I'm going to cross multiply, and I'm going to have b squared equals 100, so that means b equals plus or minus 100. And we are going to exclude the negative only because the question literally said two positive numbers. So that's why I'm getting rid of that. But there's actually another reason, and the best way to see that is Desmos. So here's what the graph looks like, and at this point I don't expect you to be able to graph this, though you could. Here's our coordinate. That's a minimum. That's 100, and 100 plus 100 is 200. And over here, notice that that's not a minimum. That's a local maximum. So if we included negative numbers, we'd have to also accept all these negative numbers, which go off to negative infinity in both sort of straight down and off to the left. So basically, once we get our A values, B values 100, I just simply put it back into our original equation. In other words, 10,000 divided by 100 is 100, and there you go. So another really tricky problem. Okay. Oh shoot, I can. I wonder if I can get. Okay. I'm hoping I can get rid of this stuff here. For some reason, that is not going anywhere. Too bad. Okay, another really tricky problem. So read this problem, read it carefully, and then begin the problem and then check this video afterward. Okay, welcome back. So this says if 2,700 centimeters of material is available to make a box with a square base, and open top, no top on the top. Find the largest possible volume. So right off the bat, we need to be thinking about volume, which is base times height times length, and surface area, which we're going to co-construct together on the next slide. So those are our two variables, or equations, I should say. So start off with a really great drawing. Okay, so we know for surface area, how many faces are a square? Just the bottom. That's why we have one of those. What's this dimension here? This is x by h. How many of those do we have? We have 4 of them. We can see 4 of them, and that's why we have 4xh. There are 4 of those. So here is my volume equation, and we know it's x times h because it's a square base. And then what we're going to do is, notice over here, we're going to say, hey, we have these 2 equations, too many variables there, and we're trying to maximize the volume. So what I need to do here is rearrange this. What would be easier to solve for, x or h? I'm hoping you're saying h because I don't want to have to create a square root. So I'm going to take the x squared to the other side. I'm going to divide everything by 4x, and then I get this piece. And then I'm going to sub it in right for h, which is going to give me that. And that's what I did there. So you can see that I've done that. Question. Now what we need to do is maximize the volume, which means there must be some volume that has maximum, that's maximum. Okay. Is this a good time to take the derivative with the x squared in the brackets? Do you want to be doing both the product rule and the quotient rule embedded? I hope you're saying no. So let's go back to grade 9, probably 10, grade 9, 10, or 11, and make sure that we can expand out. So I guess I simplified. But you could have just as easily expanded out, but I simplified first. So the x squared and the x cancel, giving me this. Now I'm going to expand, giving me this. Is this a good time to take the derivative? I'd like to say no. Can't you see that this is this minus that? So I'm going to split that fraction up. So 2700x divided by 4 gives me that. I'm going to take the derivative of this, which is now pretty straightforward. So 675 minus 3/4 x squared. Set it equal to 0 because we're looking for that slope when the slope is 0. And we're going to rearrange. I'm going to multiply by 4, divide by 3. So I'm going to have x squared equals 900 and x equals plus or minus 330. And of course, a negative value makes no sense. I can take this 30 and put it back into this equation here to find the other values. Let's take a look at what it looks like on Desmos. And remember, all I was doing there is just putting that equation there into Desmos. So x squared bracket big fat mess into Desmos, and it looks like this. Can you see the big fat mess right there? Can you see that there's a maximum right there with a width of 30, and there's the maximum volume there of 13,500. Okay, so there you go. So hopefully that helps you out. And obviously, once again, a really tricky problem. Don't forget that at this stage in the course, you should be able to really finish off your digital portfolio because we've done modeling so many times, and you've been, because of how we're learning in the active learning environment where you're working with different partners every day on problems you don't know how to do every day, you are taking risks every single day. So I hope that went well for you, and we'll check in soon.